So in this video, we're going to take a little more of a modern look at the history of atomic structure, and we're going to look at atomism in the scientific revolution up through John Dalton, who made some fairly significant contributions for us. Last time we looked at ancient atomism, primarily Greek philosophy, Democritus, and our kind of earliest writings in Western philosophy about atomism, and we briefly talked about some Eastern traditions in atomism. Again, this all breaks down to the idea that there are two possibilities for the fundamental structure of matter. Either matter is infinitely divisible, or there is some fundamental particle which, by its very nature, resists cutting. As we kind of dive into the scientific revolution, and if you think about the massive time jump here, we were in the last video talking about hundreds of years BCE, and now we are talking about the 1600s, primarily in Europe. And the place to start when discussing kind of theoretical frameworks of atomism in the scientific revolution is with René Descartes. Descartes is famous for a line in one of his writings where the French philosopher once said, "Je pense donc j'y suis." Any of you taking French might be able to pick part of that apart. In his more formal writings, he would have written in Latin, and in Latin, this same phrase is cogito ergo sum. And those two phrases are the original writing that Descartes would have given his famous line, "I think, therefore I am." It was his reduction to what he called first philosophies, the idea that if you can strip away all of the things that you might be speculating about, what's the one first thing that you can know for certain? And that thing that he can know for certain is, can't ask a question if you're not a thing there to ask the question. I think, therefore I am. And following this trail to what he then could know after that, Descartes developed, or was one of the early developers of, what is known as the mechanical philosophy. Essentially, that the universe is just a system of wheels and gears and motors churning about by some fundamental set of rules that if we know the position of particles and initial conditions, that we can predict all future outcomes because the universe is just in fact a large machine. One of Descartes' theoretical frameworks then about why things happened in the universe, specifically things like planets rotating around each other in the solar system, where there were a series of vortexes of matter moving about, and that those vortexes were the primary forces that carried things, and that the things that were carried within those vortexes were corpuscles, or particles of matter. And so these corpuscles are kind of an early scientific revolution idea of fundamental particles, although Descartes himself never referred to them as atoms. A contemporary of Descartes, or at least ever so slightly overlapping, was the chemist Robert Boyle, who wrote in one of his books called The Skeptical Chemist. And if you look down there at the bottom of the screen, it's kind of interesting to see how that's spelled. So language hasn't been formalized into kind of our modern spellings yet. So chemist there spelled Chymist. But in The Skeptical Chemist, he's considering this idea of atoms or elements. And this is often given in textbooks as one of the early definitions of an element. And he says, "I now mean by elements certain primitive and simple or perfectly unmingled bodies, which not being made of other bodies or of one another, are the ingredients of which all those called perfectly mixed bodies are immediately compounded, into which they are ultimately dissolved." So again, these elements he's talking about being small particles that are not made of anything else, meaning they cannot be cut down any further. And anything that is compounded, the individual parts of those compounded things are these elements. Again, it's funny that this is usually given as one of the early definitions of atoms, because if you read the very next line in this book by Robert Boyle, he says, if this is the definition of these things, then I don't think there's anything that meets with this definition. He's very unclear if this idea of corpuscles or fundamental particles is going to get anybody very far. We jump about 100 years later here, and we look at a guy by the name of Antoine Lavoisier. Now, we've already taken a little peek at Lavoisier before. Lavoisier is the one who gave us the metric system in combination with a number of other scientists, contemporary scientists in France. So Lavoisier pushed fairly hard for the metric system. He was a French aristocrat, tax collector, and if you notice his time of death, which I think we mentioned before, 1794. 1794 is not a really good time to be an aristocrat or a tax collector in France, because that time period is known in France as the Reign of Terror. And in his aristocratic tax collecting day-to-day life, Lavoisier made a lot of enemies who came to power in the Reign of Terror, and he ended his life a head shorter than he was when he lived his life, lost his head to the guillotine. But he also is talking about this term element or fundamental particle that Boyle is talking about, and he says, if by the term element we mean to express those simple and individual atoms of which matter is composed, it is extremely probable that we know nothing about them. But if we apply the term element, or principles of bodies, to express our ideas of the last point which analysis is capable of reaching, we must admit as elements all the substances into which we are capable, by any means, to reduce bodies by decomposition. Lavoisier is going to stop having the philosophical argument about infinite divisibility or fundamental particles. He says, you want atoms? Great, let's have atoms. Atoms are the smallest thing that we can get to chemically today. So whatever you can break things down into, and the point at which you cannot break them down anymore, we're going to call those atoms. But if we get better at doing our job tomorrow and can break that thing down, well, then it's not an atom anymore. He's going to get very operational about this. If it's the smallest thing you can break things down into, we're going to put it in the classification of atoms until we can break that thing down, and then it won't be an atom anymore. Whatever we broke it down into will be an atom. And so Lavoisier is wanting to get on with the business of doing chemistry without having to have philosophical arguments about what the pieces and parts are. Lavoisier is very interested in making sure things are named properly. He's very interested in doing careful experimentation where everything has to be weighed and measured precisely. But what exactly it is he's weighing and measuring on a philosophical level, he's less concerned with having that argument. Across the English Channel, as it were, John Dalton, who would have more or less come after Lavoisier, although he references Lavoisier a fair bit in his writings, and is willing to have that kind of operational approach, and yet he extends a little bit beyond it. Dalton was extremely fascinated by meteorology and spent his life recording the weather patterns in Manchester, England daily for decades. When we talk about how we know that climate is changing, we know that climate is changing because the long-term measurement of day-to-day observations that Dalton took allow us to generate a theoretical framework of, or a descriptive framework of the climate in Manchester, England over that long time period. And those detailed measurements, along with other people that would have been involved in or interested in meteorology, allow us to piece together a historical description of climate and compare it to climate today. Within the context of meteorology, one of the big questions that Dalton had is the mixing of different types of air a chemical or a physical process? And why, if it's a physical process, do they not separate out? Where the heavy molecules of air go to the bottom and the light molecules of air go to the top? Because air is fairly well mixed. A little less than 20% oxygen, a little less than 80% nitrogen, some carbon dioxide, some water vapor, some argon gas. All of this stuff is kind of floating about in the air, other trace gases, but they're all pretty well mixed. And any sample of air at any point is going to give you roughly the same percentages. And so how is this the case? And so Dalton went about digging into that question, and he came up with two things. One is what we refer to as Dalton's law of partial pressures, which explains the mixing of gases and the pressures that they exert as a result. That we'll get into a little bit later in the year, but right now we want to talk about Dalton's atomic theory, because if gases are physically mixing in equal proportions all throughout the atmosphere, well then, what are the fundamental particles that are mixing? And for Dalton, it became fairly clear that the atoms of Greek philosophy, at least he's borrowing the term, the atoms of Greek philosophy have to be a thing. At least the fact that there is some uncuttable fundamental process or particle that's mixing in whole number ratios and is always the same in every air sample. So, Dalton's atomic theory. There are 4 parts to Dalton's atomic theory, and all of these need to get filed away in your brain somehow, some way. This is just one of those things I'm going to want you to know. Part 1, all matter is composed of submicroscopic, indivisible, indestructible atoms with liberty and justice for all. He actually never said that liberty and justice for all bit. It always just seems to follow the indivisible. So, Dalton is telling us not there might be atoms or let's consider atoms. Dalton is now stating his theoretical framework of the mixing of gases only works if. And so because it works really well, there must be. He is stating, he's no longer skirting the philosophical argument. He's saying, there is no argument. Atoms have to be a thing. Second thing, all atoms of the same element are identical. So every oxygen is like every other oxygen. His third statement is atoms combine to form compounds in simple whole number ratios. That means atoms are like Legos. When they mix together in whole number ratios. You can't have parts of Legos. Parts of Legos are shattered pieces of plastic. Atoms are the same way. There's no such thing as half a nitrogen. There's no such thing as half an oxygen. Half an oxygen would be a beryllium because it would have half as many protons. And then the last statement, chemical reactions occur when atoms are joined, separated, or rearranged. Now, it's not on the screen, but you need to take a second and you need to write this down with this statement. Atoms of one element cannot be converted to atoms of another element by chemical reaction. Let's say that again. Atoms of one element cannot be converted into the atoms of another element by chemical reaction. Chemical reactions are only happening when atoms are rearranging. It cannot cause a change in the type and number of atoms. Atoms are conserved in any chemical process. Now, this is Dalton's atomic theory. Modern atomic theory is pretty darn close to this, but there are two things that Dalton got wrong. One of them, atoms are not indivisible. Atoms are in fact divisible, and we can break them down into subatomic particles. I think most of you probably already know what those are. Protons, neutrons, and electrons. And as we said earlier in this series, we can even break the protons and neutrons down into things that are smaller. And atoms of the same element are identical, which of course they're not. Atoms of the same element occur in different types that are known as isotopes. Isotopes are elements that have the same number of protons but different numbers of neutrons. So it's protons that define the atom. Isotopes are different variants within the same type of element. But here's the thing. Even these slight errors in Dalton's atomic theory are still part of modern atomic theory if you add a few more words here. All matter is composed of atoms, which are submicroscopic and indivisible chemically. You cannot break atoms down by chemical reactions. It takes nuclear reactions to break an atom down. And all atoms of the same element are identical chemically. Even though there are different versions of the same atom with different numbers of neutrons, because they have the same number of protons and electrons, those elements react chemically the same way, regardless of their slightly different flavor, if you will. Not only that, but Dalton's atomic theory is not modern atomic theory in a bunch of important ways. He's just starting to grapple with this idea of atoms, and he doesn't quite have it all sorted. His famous work is called A New System of Chemical Philosophy. It was actually first produced in 1808, but there was a second kind of book produced a few years later. But this is one of the diagrams of what would have been his periodic table. Notice the symbols are slightly different than the symbols that we know today. Rather than having the letter symbols, Dalton really wanted to have these kind of circular atoms, which all have, which essentially is what he said they were. They were little tiny spheres that clumped together in these secondary clusters. And if you look over here on the side, you kind of see his compounds. But here's where the terminology breaks down a little bit, because we have the top part of this table, the elements that he would refer to as simple atoms, but then there were also compounded atoms. Within his work, he would talk about atoms of water. And so he's really talking about what we're going to later refer to as fundamental particles. Formula units as another term that we will use, rather than atoms in a modern elemental sense. So he introduces this idea, he gives us a chance to refine it over the years, but for Dalton this is still kind of fairly hazy on how this is going to all come together. In our next video we're going to look at some historic models of the atom, and there are actually going to be 4 that I want you to know, but as a side note we're going to call this the Zeroth Model. And it's Dalton's atom, and it is a spherical object floating about in space, clumping together in clusters. And so to ask the following question, what's in Dalton's atom? If your knee-jerk reaction is to say protons, neutrons, and electrons, you got to put the brakes on, because Dalton will not even allow you to ask the question, what's in the atom? For Dalton, the atom is fundamental. It's uncuttable. It's indivisible. There is nothing in the atom. And this is the model that we're going to be working with over the 19th century, throughout the 1800s. We're kind of envisioning the atom as this fundamental particle. And then as we develop new tools, we start finding out, wait a minute, it's just a little more complicated than that.